Assalamualaikum and hi. Welcome to this video presentation on CHM361. We are going to present about single atom catalyst. In this case, it is about platinum on Fe2O3, which is hematite. In this case, we are going to present about metal support configuration and geometric stabilization on metal oxide. The objectives of this presentation is to relate the special characteristic of the block elements which have variable oxidation states and surface catalysis to single atom catalyst. To explain the side digging structural configuration where platinum cells stabilize on iron oxide, and to explain how isolated transition metal atoms interact at an orbital and lattice level on a hematite support. As an introduction, transition metal is defined as metal that have partially filled orbitals. Their specific electronic structure grants them physical and chemical properties, which allows them to be exceptional catalysts. Where traditional catalysis, which is heterogeneous, relies on large cluster of metal atoms, where only the surface layer can interact with the reactant, leaving the interior atom wasted. So in order to achieve the maximum atomic efficiency, cutting-edge research has found out that catalyst design can be let down to the ultimate limit, the single atom catalyst, which is rather than acting as a static floor, the metal oxide support interacts dynamically with the single atom to alter its electronic environment. In this case, the atom is platinum. This interaction also exploits empty or partially filled orbitals to manipulate charge distribution and optimize chemical reactivity. For the findings and discussion of this presentation, we have found the process of blast furnace, which reduces hematite, becoming viable environment for platinum to react. And the second one is platinum on hematite, second atom catalyst itself, where the process of bending and making hematite surface oxygen bond into a straight line. For the blast furnace process, hematite doesn't actually reduce to iron and carbon dioxide. Hematite is actually heated up just so enough to be able to react to platinum. To explain in detail, hematite is heated up in a bulk blast furnace. On an atomic scale, its surface serves an excellent grade for hosting noble metals such as platinum. The hematite itself treats catalyst platinum supports while also being robust and crucial active sites for the platinum itself. There is also a recent milestone study that reveals a much more aggressive phenomenon, which is known as digging its oxide. To explain this side digging to create platinum on hematite single atom catalyst, we have to reduce hematite. After hematite was reduced, platinum doesn't passively set on top of the reduced hematite. Instead, the incoming platinum atom will break three existing surfaces of the iron-oxygen bonds. As you can see in the diagram on the right, the platinum atom is overlapped on top of the iron-oxygen bonds. After that, the platinum atom forces the lattice to warp, embedding itself into the highly unique pseudolinear or Pt1 coordination geometry. While driven by the energy minimization, the platinum atom alters its electron distribution of 5d9, 661, 6s1 to find a lower energy with stable configuration. To go into details of platinum breaking three bonds of the iron-oxygen bonds, breaking the host bonds requires energy, but the resulting dark in linear structure yields a massive benefits, which is lowering configuration energy. As you can see in this diagram, the platinum will break 3 bonds and then replaces the 3 bonds with Pt1 pseudolinear structure. As you can see, the energy will also lowers down from negative 2.72 eV into negative 4.23 eV. This also has created some benefits, which are preventing sintering, where this local bond gives the catalyst exceptional thermal stability, preventing isolated platinum atoms from migrating and clumping together. It also preserves the reactivity of these bonds, where the transition metal accommodates variable oxidation states of this linear Pt1 link, also leaves open and highly accessible pathways for gas phase reactants to adsorb and react with this bond.
Now let's look at some real-world application of Pt1/Fe2O3 single atom catalyst. The first application is in the oxygen reduction reaction, which is one of the key reactions in hydrogen fuel cell and zinc air battery. This reaction is usually slow, so an efficient catalyst is needed to increase the reaction rate. Research has shown that platinum supported on hematite forms stable PTFE active site. This site improve oxygen absorption and help break the oxygen-oxygen bond more efficiently. As a result, fuel cell can produce energy more efficiently while using a much smaller amount of platinum, making the technology more cost effective. The second application is carbon monoxide oxidation for vehicle at house purification. Carbon monoxide is a toxic gas produced during fuel combustion. The interaction between platinum and iron oxide creates active PTFEO site that can absorb bond carbon monoxide and oxygen molecule. This allows carbon monoxide to be converted into carbon dioxide more efficiently, helping to reduce harmful emission from vehicle and improve air quality. Final application is environmental remediation, particularly in the reduction of 4-nitrophenol, which is a common industrial water pollutant. Studies have shown that highly depermeable platinum atom on alpha Fe2O3 exhibit excellent catalytic activity in converting 4-nitrophenol into 4-aminophenol. This reaction is important because 4-aminophenol is a valuable chemical used in the production of pharmaceuticals such as paracetamol. Therefore, this catalyst not only help remove pollutants from wastewater but also produce useful industrial chemicals. So, in conclusion, Pt1/Fe2O3 single atom catalyst show how the unique properties of transition metal can be used to improve catalyst performance. Unlike traditional catalysts, platinum atoms do not just stay on the surface. They create their own stable position by forming a linear O-Pt-O structure on the hematite support. This creates the catalyst more stable and prevent the platinum atoms from clumping together. Because each platinum atom acts as an active site, that catalyst uses platinum more efficiently while still maintaining high catalytic activity. This means better performance with less platinum, which can also help reduce costs. As we have seen, this catalyst has many important applications, including fuel cell, vehicle hothouse purification, and wastewater treatment. These applications show that single atom catalysts have a great potential for clean energy and environmental protection. Overall, understanding how platinum interacts with the hematite surface help scientists design better catalysts that are more efficient, more stable, and more sustainable for future technology.
That is all for this video presentation. We hope you have learned something new about single atom catalyst. You can also ask us some question in the comments below. Thank you.